This is the last of the videos on chapter 3. We'll be shifting gears from looking at Lewis structures to masses, molar masses. So our goal is no longer to be taking the molecular formula and moving to some Lewis structure and then maybe shaping it. And that's a very important skill to be able to do. But our goal is to build on what you learned from the first test, and that is how to take and determine from maybe some mass that you measure in the lab of an element like aluminum and find out how many atoms you have of that aluminum. So that molar mass bridge or atomic mass bridge, we said, connects the macro scale, which you can weigh in your hands, to the numbers of atoms and such that you cannot put in your hand. That's the micro scale. So macro scale to micro scale. We're picking up with that again. So if we have some compound that we have to deal with, we just simply add up all the atomic masses. And we've talked about that in just a slight application to things like CO2 or water. We can add up one carbon, its atomic mass, and two oxygens, its atomic mass. And we can add those up to have the molar mass of the compound. So that's what we can use those individual masses for. So for example, if we have water that we're looking at, we can determine its molar mass by taking that of the atomic mass of hydrogen. And there's two of them, so we multiply that by 2, and we add to it the atomic mass of oxygen, which is around 16, to then capture all of the mass of 1 mole of water, which would have 2 moles of hydrogen, and it would have 1 mole of oxygen. So that would give us a total mass of 18.02. And this would be the molar mass of water, be 18.02 grams. So we can do this for any compound, whether it be ionic or covalent. So in this case, we have lithium carbonate, and we have to know that's one of those polyatomic ions. You'll have to know carbonate has 1 carbon and 3 oxygens, and more importantly, it has a -2 charge. So we have to know that we have 2 lithiums so that it can cancel the -2 charge of carbonate. We can have 2 of those to do that. So this is our formula. This is the ionic formula for lithium carbonate. So we can add up by multiplying the molar mass of lithium by 2. The molar mass of carbon, there's only 1 of them, so we only need to take the molar mass of just carbon itself, which is 12. And then we can also then take the 3 times the molar mass of oxygen to get our final molar mass. So I'm just going to take and look at, if we consider hydrogen, our lithium, look at it through a periodic table. We can find that in a reference, either website, or in this case I'll find it here in my book. It says 6.941, so I will take then 2 times this 6.941. I'll add to it the 12.00 grams that we have for 1 carbon, so 1 times that, and 3 times roughly our 16.00 grams. And again, you'll look at your periodic table for carbon. We said it's around 12, and then it's 16 for oxygen. And we would add those up. So we can take our 2 times the 6.941, and we would get 13.882. 12 times 1 is just 12, and then 16 times 3, we can say that's 48. And again, your sig figs, we would keep as many as we can. We multiply. These are just whole numbers. So we'd say, well, we have 4 here, we have 4 here, we have 4 here. We can add all that up, and we would get then, if we do that, you would get something around 70 or 80. Let's do that. So 13.882 plus our 12 plus our 48 equals 73.882, and I'll just leave it at 73.8 grams. So that's our molar mass of lithium carbonate. We can do that with any compound, so I'm not going to do that with all of these that are about to go through, but I'll just give you the idea that if we have aspirin, it'd be 9 carbons, 8 hydrogens, and 4 oxygens. You would add all that up. The weights of 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen, because if we have 1 mole of aspirin, it has within it 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. Now, we'll wait in class. There's a miltefosine. There's a story behind this particular ionic compound. It has a structure where we have a salt within it. It's an organic salt, so it has a negative charge on this oxygen here, and it has a positive charge on this nitrogen here. It's a only drug that's known to treat a particular very, aggressive, not a bacterial infection. I think it's an amoeba that is troubling kids jumping into warm water. So we'll hear the story of miltefosine and what it treats in class. But we could take up the weight of it by, again, just finding out how many of each element it has. 21 carbons, 46 hydrogens, N and 4 O's and 1 P. And we could answer the question, how many moles of carbon are present in 0.185 moles of miltefosine. Now notice we're not changing from moles to grams. So we could just say, what I'll do is I'll represent this as MF, miltefosine. We'll just say, just for sake of the math, we'll say 0.185 moles of this MF. We know that for every 1 mole of the MF, we have how many moles of carbon? We have 21. 21 moles of carbon. So we can just do that math. This is kind of setting it in a conversions along way format. You can do it other ways. But again, we tend to want to be able to learn that language of dimensional analysis. So I put it in that way where we would cancel this and know that we're right. But let's take that 0.185 now times 21. We'd say now we know that we have then in 0.185 moles of miltefosine, we have 3.885 moles of carbon. So we can do some things knowing the molar mass of miltefosine. We could go from grams to moles, or just knowing the ratio of atoms within 1 mole of miltefosine, we can change the discussion. We can say, instead of knowing what number of moles of miltefosine I have, I can also know the moles of any atom within it. Right, we're almost done. If you've hung on this long, we're moving into use of the molar mass as a bridge. So answering questions not in terms of moles to moles like we just did, but what about grams to moles, or moles back to grams, or even grams all the way down to number of atoms? So if you pick up from where we were in the first test, we said we can do this with CO2. We could say how many molecules of CO2 are combined in some number of moles of CO2, or even grams. So if we had 5 moles of CO2 as our starting point, 5.0 moles of carbon dioxide, we could say, to find the number of molecules, I would say first, the number of atoms of carbon in CO2. For every 1 mole of CO2, I have 1 mole of carbon. And everybody, I hope, would say that they would agree with that. So then we would say, okay, now it didn't ask for a number of moles of carbon. It didn't ask for that. It wanted to have number of molecules. So I can say, oh, well, I need to have 1 mole of carbon on the bottom to cancel that out. And I can say for that 1 mole of carbon, I know there's always 6.02 times 10 to the 23rd carbon atoms. So we can do that. 1 mole of carbon, I know, has 6.02 times 10 to the 23rd carbon atoms. And that would give us our answer. So we can just say X, and we could solve for that. And that would give us our final answer. I'll leave that for the math for you to do, but that's how we went from, in this case, the number of moles of copper. We went from number of moles of carbon dioxide to the number of molecules of not CO2. We changed this, so we went to the number of atoms